Welcome, everyone. Let's dive straight into this explainer. Today, we're going to definitively shatter one of the most persistent engineering myths out there about lightning. We're unpacking the real science of protecting structures from one of nature's absolute most violent forces. You know, it's not magic, it's definitely not guesswork, and as you're going to see, it is absolutely not about attracting a storm. Here's our roadmap for today. We'll cover the great lightning myth, anatomy of a strike, the single rod fallacy, engineering parallel paths, and finally, the 5 pillars of protection. Let's get right into it. Part 1. The great lightning myth, illusion versus reality. To understand how we actually protect buildings, we first gotta unlearn the single most common misconception that's out there. Look at the stark contrast here. On the left, we've got the illusion, this idea that a lightning rod acts like some kind of giant magnet, actively pulling lightning from miles away to create a strike that wouldn't have otherwise happened. Let me be clear, that is completely false. A lightning protection system doesn't create the thunderstorm, and it doesn't increase your chances of being struck. Now look over at the right. The reality is, the system simply provides a controlled, safe attachment point when a strike in your immediate area is already inevitable. It's not inviting the strike, it's just managing it. Moving on to part 2, anatomy of a strike. To see exactly why having that local attachment point matters so much, we need to break down the literal physics of what happens in the milliseconds before a flash lights up the sky. A strike isn't just a solitary bolt shooting down from the heavens. It's actually more like a high-speed negotiation between the sky and the ground. First, you have the downward approach, called a stepped leader, descending from the cloud in these short, jagged steps. As it gets closer, the electric field on the ground intensifies like crazy. This triggers the upward response. Upward streamers start rising from multiple objects on the ground: chimneys, trees, antennas, and yeah, lightning rods. The main current flows the exact fraction of a second that one of those upward streamers finally connects with the downward leader. Visualizing the sequence, you can see the downward leader searching, the upward streamers reaching up in response, and then, boom, the exact moment of connection. The lightning rod doesn't dictate the whole path from the cloud. It only influences that final critical millimeter of connection when the massive discharge is already hovering right over the building. So the key takeaway here is that the electric field concentrates most heavily around elevated and pointed objects. By placing a properly positioned air termination conductor on a roof, we are purposefully creating a preferred upward streamer origin point. We want that rod to win the race, right? We want it to intercept the strike before an upward streamer can form from a vulnerable chimney, a delicate solar panel, or the edge of a flammable roof covering. We can't stop a thunderstorm, but by comparing an uncontrolled structure to a controlled one, we can absolutely control the inevitable. Without a system, lightning attaches totally at random to vulnerable parts of a home. But with a proper air termination system, we create a calculated protected zone. Think of it like a protective dome. The vulnerable elements stay safely tucked inside this volume, completely untouched, while the rod intercepts all that raw energy above them. Part 3. The single rod fallacy. Here's a surprising truth. Just throwing a piece of iron on a roof without a comprehensive system isn't just ineffective, it's actually incredibly dangerous. Think about it. If you intercept a strike but only give it one single down conductor route to the ground, you're essentially creating a massive electrical traffic jam. You're forcing a violent current, we're talking up to 100 kiloamps, into a dangerous bottleneck. This single path causes intense electromagnetic fields, massive voltage spikes along the wire, and hugely increases the risk of the current violently jumping right out of the wire and into your home's internal wiring. To really understand why this happens, we gotta look at the math. Lightning is not your ordinary 50 Hz household electricity. It rises insanely fast. Because of that sheer speed, we have to calculate what's called inductive voltage, which is U equals L times dI over dt. In plain English, this means the physical geometry and the routing of our wire is just as critical as how thick it is. A sharp bend creates a massive inductive bottleneck, causing the voltage to spike to literal explosive levels, completely regardless of the wire's electrical resistance. Take a look at the inductive speed bump on the right. If we use long conductors with sharp 90-degree horizontal bends, that rapid change in current creates an extreme voltage spike right at the corner. The energy has nowhere to go, so it literally forces the current to jump out of its intended path and into nearby conductive materials, like internal plumbing or electrical systems. This terrifying event is called a side flash. Path A, that smooth, direct route, is exactly what we must achieve to avoid this disaster. Which brings us to part 4, engineering parallel paths. To safely manage this incredibly violent and fast current without causing a side flash, engineers have to follow the golden rule of electrical defense, which is divide and conquer. By distributing multiple down conductors symmetrically around the perimeter of the building, we take that massive 100 killiamp current and divide it into smaller, much more manageable fractions. More parallel paths mean a lower current per conductor. This vastly reduces the voltage rise, minimizes electromagnetic interference, and pretty much neutralizes the risk of those explosive side flashes we just talked about. Because of this, routing these paths becomes an absolute science, and there are strict rules. We absolutely must avoid creating unnecessary horizontal loops, using sharp bends, or routing these exterior wires anywhere near internal electrical cables. Instead, we always prioritize the absolute shortest, most direct route to Earth, distributing the down conductors symmetrically and rigidly maintaining calculated separation distances from any internal metal. This routing checklist really spells it out. On the left, you see exactly what turns a protection system into a hazard. Loops, sharp bends, getting way too close to internal wiring. On the right is the safe engineering standard. Direct paths, symmetrical distribution, and most importantly, maintaining strict separation distances. We've got to ensure that the massive surge of energy traveling on the outside of the building never, ever induces lethal voltages on the inside. Part 5, the 5 pillars of protection. Now that we understand the physics of the strike and the math behind the current, let's put it all together into a complete structural solution. A true, modern engineering solution isn't just one component. It's a holistic system that relies entirely on these 5 distinct, non-negotiable pillars working perfectly together. The air termination system on the roof, the down conductors on the walls, the earth termination system in the ground, equipotential bonding throughout the structure, and surge protective devices at the electrical panels. Let's dive into how this evolves. We graduate way past the myth of just slapping an iron rod on a roof. We expand that single rod into a network and then integrate that network into a complete building-wide mesh. It completely envelops the structure, intercepting the strike at the top, conducting it safely down the sides, and driving it deep into the foundation. But the job isn't over when the lightning hits the dirt. Once the current reaches the earth termination system, it has to safely disperse into the soil using foundation or ring electrodes. At the same time, we've got to protect the electrical grid. Equipotential bonding and surge protective devices, or SPDs, act as heavy-duty bouncers here. They block any lethal transient overvoltages from sneaking back up into the house through your water pipes, internet cables, or main electrical panels. They equalize the voltage and keep your sensitive electronics from getting totally fried. Ultimately, what we're looking at is an unbroken, beautifully coordinated chain of protection. It starts with interception at the highest point, moves to conduction down the facade, handles earth dispersion below ground, and relies on bonding and surge protection to secure the interior. It is this exact sequence that successfully tames the raw power of nature. A failure in just one of these links compromises the entire building. We can't stop the storm, and we certainly can't prevent lightning from striking. But as you look at the buildings around you today, your home, your office, your kid's school, ask yourself a critical question. Do they just have a dangerous, decorative single rod on the roof? Or are they truly engineered with a complete 5-pillar system to safely control the inevitable? Thanks for joining me on this explainer, and I really hope this changes how you look at the skyline during your next thunderstorm.